What I'm going to do today, brief agenda. Uh, the first thing I want to do is sort of set foundation to make sure we're talking about the same thing. So, what does that mean? Well, we have to define what our objective is. When we're using econometrics, what is our goal really? What problems are we trying to solve? Once we kind of have common foundation and common framework for this conversation, then I'll work through the toolkit of different things you can do in terms of the design of a research study, paired with appropriate estimators from econometrics, and what assumptions each of those depends on for accomplishing the goal that I set out at the beginning. And then I'm going to wrap up at the end with the part that might be actually most interesting for people, which is a whole bunch of normative things about information systems journals when you try to publish a paper using these methods, stuff that's not written down in a textbook, but that the discipline kind of norms have formed. People expect to see these things. And if you don't show them, you're going to have more friction in the review process than is necessary. That's probably where I suspect a lot of the Q&A is going to go. But accrue your questions and we'll see how this goes on the earlier parts. So hopefully this is informative. So the first thing is, before you even think about using this method, are you using it to answer a question that it makes sense to be like, is there alignment between your objectives in your research study and this methodology? So the main thing I would say that I often encounter when I'm handling papers as an editor that is immediately jarring and problematic is when people have used econometric techniques that sort of have the error of a causal inference objective, but they're actually kind of studying a prediction problem. They want to see if like these variables are going to be meaningfully associated with this thing that I'd like to be able to anticipate whether it's going to happen or not. The first thing you need to do for yourself is be very clear. What exactly is the objective of your paper? Is your goal to show a causal relationship from one variable on another? Or is your goal just to show an association? If your goal is not causality, you shouldn't really be using this stuff. Or at the very least, when you do use it, you need to talk about it the right way. So there's a very useful paper that I dropped in advance of the talk. One of the papers I directed people to read by Galit Shmuley, who's now at Taiwan, I think National University in Taiwan. Very interesting paper from back in like 2010, basically setting out a framework for thinking about what is the difference between prediction and causal inference, right? So I rarely recommend that people read that. This is something I give to PhD students to read when I teach PhD seminars on these methods, is getting clarity in your head about what kind of question are you answering and then using the appropriate methods for that question. So if you do decide you are working on a causal question where it is important, like the implications depend on showing a causal effect, you really should be careful with your choice of words and terminology and the way you write about those things in your paper. So I would specifically recommend you avoiding ambiguous terminology like the words association or relationship, which might just be correlational or predictive, and really talk about effects and impacts and consequences. Take a stance. The worst thing you can do is try to tread the middle, basically kind of acknowledging that your paper isn't getting at a causal effect necessarily, but then sometimes talking about it as though it's causal. If you try to split that and thread that needle, you're going to fail, and it is often a recipe for disaster. So take a stance and then argue that stance in the paper. Okay? So that's my first top level point. So I'm assuming we're working on causal questions, and that is our goal, and that's what our belief is going to be about the findings in the paper now. So if our goal is to arrive at a causal relationship, there's two things that we generally worry about from a sort of causal inference econometric perspective. One is threats to causal inference, which are essentially endogeneity. I know this word gets thrown around a lot and people get sick of hearing about it in the review process, but the reality is, from a methodological perspective, it is like the primary thing that you're worried about if somebody's trying to draw a causal inference from data. I'll talk about what endogeneity means in a second. There is a second thing that we worry about, but it honestly doesn't get anywhere near as much attention, despite that it can be just as bad in terms of the effects it has on your ability to make meaningful inferences, which is your model specified correctly? What that means, you always have to be thinking about um, what the oracle perspective on the data generating process. So the variables that I see are manifestations of true things that I don't necessarily see them perfectly, but an oracle could. And the oracle, like if you were an oracle and could see exactly what was going on, there would be a true data generating process. There would be, this thing happens first. I have temporal precedence. That has a causal impact on this next thing. This is the sequence. You can think about directed acyclic graphs, which are essentially how constructs or measures of constructs relate to each other causally in a framework where you might see feedback loops between things or where you might see a causal chain. You think about that sort of visual representation of the chain of causality. That's your mental model of how things work. The way you set up your regression with your measures needs to reflect the mental model. If they don't line up, so let's say this, variable number one has a exponential or multiplicative effect on variable number two. When this thing goes up by one, it causes this thing to go up by two. This goes up by two, this goes up by four. If you then specify that as this has a linear effect on this other thing, that's a model misspecification. And now you're already misaligned with the data generating process and things are going to go bad. That's not usually where the focus is in most social science papers, despite that this is a real issue. So I'm going to focus more on number one, endogeneity concerns, because it is primary, honestly, and it is the thing that gets the most attention in the review process. Okay, so what does endogeneity mean? So there's the literal definition, which is essentially internal to the system. That's what the word refers to. And there's a reason we refer to causal identification problems as being endogeneity problems. It is generally the case that the problems we're talking about are possible paths of influence where the thing I'm studying the effect of, my treatment, my X variable, sorry, I'm not raising my hand on purpose, my right-hand side variable of interest, that it is not external to the system, that it actually has inbound causal effects from other things that I'm studying in my system. That's bad because it becomes really difficult to isolate the causal effect of the thing I care about, X in these diagrams, on the outcome of interest, Y. So there's various ways that this can happen. I'm showing you two examples here. The example on the top is an example of omitted variable bias or confounding, where there's some unobserved common cause that jointly drives both X and Y. I don't see it. X might have no relationship to Y whatsoever, but when I run a regression or an analysis, I see an effect. And that's not because X has a causal effect. It's because there's a common factor I'm not seeing that I'm actually picking up on that makes it look like there's a relationship between X and Y. The one on the bottom is reverse causality. So X might cause Y, but Y also causes X. This becomes a problem because it becomes a challenge for me to disentangle. Is the relationship I'm picking up in my regression, is it coming from X's effect on Y or the other way around? I can't actually disentangle those two things, then I can't really attribute or figure out what's X's causal effect. Okay, so endogeneity is all about data generating processes that are not properly accounted for in my regressions, which then mess with my ability to properly isolate and infer the causal impact of X on Y. Okay, and it's all about being internal to the system, or hence endogenous. So there's three types of endogeneity. Nobody ever talks about the first one, which is measurement error, mostly because there's not a lot you can really do about it because the data you have is the data you have, and you never really know if measurement error is there or not. So that's not to say it doesn't matter. It's just the one that's harder to deal with. I'll come back to that one more a bit later, but essentially all this is the data available to you is not an accurate measure of the thing you actually are studying. I can give you good examples of this. People might say, get asked on a survey, report how often you take drugs. And people who don't take drugs will answer honestly. And the ones who do might be concerned about where that data is going to end up. And as a result, they don't answer honestly. And now you're getting measurement error. If you then use this variable to study some other, its effect on something else, the measure's wrong. And as a result, you're going to get biased estimates of how this variable, if you could measure it, what its effect would be on something else. It's not going to be accurate anymore. So that's one I'll come back to. It's fairly intuitive that if you have error in a variable, you're not getting an appropriate measure of it, therefore you're not studying its effects properly. Number two and number three were the ones I just showed you pictures of on the last slide. So reverse causality, otherwise known as simultaneity, is simultaneous effects. Y causes X and X causes Y at the same time. It's problematic for the reason I mentioned a second ago. I can't isolate the one path from X to Y because I'm seeing them both jointly at the same time. And then confounding, as I mentioned, is the one people usually think most about and first about. And it's the one that comes up the most often because it's the easiest one to think about, which is common unobserved causes. Right? So everything we do in research design is thinking about how to deal with these problems. Okay. Econometrics doesn't solve these problems. Econometrics applies a research design in the form of sort of an estimator. It's an implementation of the research design. Really, what we need to think about first conceptually is how are we going to set up our analysis in a way where I can convince people that none of these three things are going to be a problem. It's going to be argument based, actually. Okay, so just to give a little bit more intuition before we move on, bias from confounding, very common example of this, the effect of smoking on health. If you didn't think too hard about this, you might just look at, or sorry, I think a better one to talk about is probably the effect of coffee on health. Historically, I would say there's, movies about this, coffee and cigarettes, right? This kind of thing. So these were things that often would be consumed together. Quite often, people would go for coffee and they would smoke. And because these things were often consumed jointly, if you just study the effect of coffee on health and you ignore the role of smoking, you might find a very negative effect of coffee on someone's health. But then as soon as you realize that coffee drinkers often tend to smoke too, you realize that that common cause, right, common association might be the real issue at hand. You control for it or you deal with it, and now you find maybe positive effects of coffee on health, right? So that's confounding. That's a fairly intuitive one. The other big example that people get right away, you might find an association between ice cream consumption and pool drownings, but of course the common cause is heat, and it's the weather, okay? Simultaneity, there's lots of good examples of how this can manifest. A good one is the Matthew effect, sort of the rich get richer kind of effect. So if I do well, I succeed. If I succeed, I have more resources and therefore I do well. And basically you get this feedback loop. And breaking that feedback loop is the challenge to try to understand the first effect in the loop. Okay. So simultaneity is all about feedback loops. And then measurement error, I mentioned a second ago. So measurement error in your outcome variable, if it is random, generally doesn't matter. So it basically will impede your ability to find an effect of X because you're not actually measuring it properly, or if you're measuring it noisily in the outcome, it's just harder to find that relationship. Measurement error in X is usually a bigger problem. Okay, that's one that people are most worried about. If the error in your X variable is random, which is a big assumption, but let's just say that's the case. If your error is just noise on top of X, that's still bad. You can't ignore that. The reason is you're looking at all this variation in X. Some of it is fake and by construction not related to Y. Some of it is valid. But because you have mixed in this invalid variance that's not really there, you're only picking up on part of X's effect when you use this noisy measure. And as a result, you're going to understate the effect that X actually has on Y. Okay, so the noise is basically impeding your ability to pick up on the true magnitude of the effect. It results in what's called attenuation bias. This is the one that gets talked about most in textbooks because it's the easiest one to demonstrate what will happen mathematically. Now, assuming random noise is a big assumption. There's no reason to believe that most of the time. I gave an example earlier that of measurement error that was not random. Like people have social desirability biases in surveys. They're going to lie when they don't think specifically that you're going to like their answer, and they'll tell the truth when they think you're going to like their answer. So you get very skewed measurement error. It's often hard to have any idea ahead of time what that's going to do to a particular causal effect because it depends on the nature of the systematic measurement error and how it associates with the outcome and X's true value. It can bias things in all kinds of different ways. This is the hardest one to deal with because you often don't know for sure that it's happening. So this is one where you're you need to have a convincing explanation. Where did your data come from? Where did this measure arise? And how is it collected to be able to make a good case that it isn't going to be incorporating error? There's a QR code there you can check out. One interesting example of measurement error in the IS literature. Uh, these days, people often, or not often, may use machine learning generated variables. I have images of people. I predict their gender from their photo, things like this. And then I use that in a causal regression later. Those predictions have inherent measurement error because unless the predictive model is perfect, it will have prediction error. And that prediction error becomes measurement error in my causal regression. So that's the point of that paper. And actually, we have a stream of literature or papers following that original paper that deals with that specific problem, how to correct measurement error from machine learning generated variables in causal regressions. You can do correction in that unique setting because that's a weird situation where you actually get to see the measurement error from the machine learning training process, right? You actually get confusion matrices and things. So you know what the error actually is, and then you can do a correction in the second stage. So check that out if you're curious to know more about that or if you're doing that in your papers. Okay, so we have these three types of endogeneity: simultaneity, confounding, measurement error. Measurement error is very hard to deal with, but there are a lot of things we can do. Again, I'm signaling by accident. There's a lot of things that we can do to deal with confounding and simultaneity. So there are two general ways I think you can think about for addressing endogeneity problems or getting at causal inferences. The first thing, and often if you're thinking quantitative research, the first thing you hope to be able to do is to run some kind of randomized experiment. Now, I say this, but of course, experiments are not perfect for everything. They are ideal from a causal inference perspective. They may not be ideal for showing mechanisms. They may not be ideal for understanding any sort of nuance about what's going on. You can show a convincing causal effect with an experiment, but then explaining why it's happening is not necessarily going to be easy with this methodology. So what I'm saying here, this hierarchy is very specifically about best setting you up for a valid causal inference that people will not question, at least from a is it real perspective. So experiments are generally the preference if you can do one, right? Of course, there's a lot of things you cannot study with an experiment. An example I talked about in class yesterday. I'm studying gunshot detection technology these days. And so they put up microphones around a city, and then they use ML on audio in real time to flag gunshots and report it to the police. Huge problem with this is you don't actually know if this system works correctly because there's no way to audit it. Because what would you do to audit it? You'd love to go around and randomly fire off guns around the city at different times and then look at the labeled data and see, did it detect it properly? You'll never be able to run that experiment. It's just not going to happen. Okay. So there are situations where it's just illegal, infeasible, it's too costly, etc. So a lot of reasons you may not be able to do an experiment. So assuming you can't run an experiment, now we're thinking about other research designs. Okay, things we can do with archival data sets. So your goal with archival data and coming up with a good research design is to figure out a way of getting a clean, i.e. not endogenous, purely exogenous variation in X, your treatment, the right-hand side variable you're interested in studying the effect of on Y. So this is all about breaking inbound arrows to X, okay, in a causal diagram. So even though you may not be able to run an experiment, I always advise it's valuable to think about what would the ideal experiment be. So if cost was not an issue, if legality was not an issue, right, what would I do? That helps you think through the thing you're trying to achieve through other means via your research design. So you want to get to something that looks like that as close as possible. And it helps you think through like the things that stop you from doing that. Well, why might they matter? This thought process is often useful, is what I'm saying, right? For thinking through like the threats to the causal validity, where endogeneity might come from. You may even think about drawing a causal diagram, although I'll be honest, it's still not common that you see them in IS papers. It is still a useful exercise for you to think through the causal chain of what's going on. Once you understand this causal chain, otherwise known as your data generating process, show it to somebody else and make sure it makes sense to them too, that you're not missing something obvious. This could happen in conversation. This could also happen in a conference. This is why we present things before we submit them to journals, because you may be missing something obvious. Do this early though, getting feedback from somebody like your office mate or something to make sure that everything is kind of making sense and is defensible. Once you have some like reasonable grounding or belief on the causal chain of what's going on, now you think about, okay, what does my research design look like? And this often will happen in pairing with what is the data available to me? Because sometimes you won't be able to measure everything very well, or you may not have any measures of certain things. And then the question becomes, okay, is the data I have sufficient? Or do I need to think about a different methodology? Or do I need to go and collect some other data to make this work? Okay. Now, I understand I'm taking this from the perspective of you're sitting in isolation, you're reading papers, you're coming up with research questions, and only then do you think about data. I understand that's not always the reality. I understand sometimes you have come across an interesting phenomenon in the news that has data with it, and you're thinking about why that might be a meaningful thing to study. Obviously, practicality isn't as I'm always like completely describing here, right? Usually, there's some happy medium. It's a process of iteration in research. Uh, I advise starting from meaningful question if you can, because it tends to end up being a better paper. But if you have a great question with no data, that's not going to go anywhere. And if you have data with a bad question, that's also not going to go anywhere. So there needs to be a bit of iteration where you think about these two things together. Okay. At some point, though, you need to think about this data generating process that goes with your question and make sure that it makes sense. Once you have this mental model in your head, you can start to think about research designs. A way of thinking about this is at the end of the day, what you want is a data set and a method, right? An approach that replicates what an experiment would give you. So what would an exogenous variable, an exogenous treatment look like in a data set that came from an experiment? Well, if X is truly exogenous, then it's not going to associate with anything else in your data set except the things it affects. There are often things that you can see in your data that you know by definition could not have been affected by X because they manifested before X changed. Temporal precedence is one of the key things for causal effects, right? So often this is why you'll see sort of these balance checks or randomization checks in an experimental paper. They're doing something which is honestly a bit questionable philosophically and epistemologically, but they're trying to empirically show that there is no relationship between the treatment in the experiment and stuff that is pre-treatment, stuff that happened before the experiment started, things that should not conceptually be possible to affect with the treatment. So things like if I'm studying individuals in a lab experiment, I can look at the association between treatment and their age or treatment and their gender. There should be no effects, and I know that. So if I see an association, that's a concern. It means that X isn't exogenous. It's not randomly varying in the system. Something else is driving an association with stuff that shouldn't be there. Okay, so we see this in experimental papers often that people try to show balance. This is an example from one of my papers from a couple of years ago. Um, you can generate, in many cases, a similar balance check in your archival data following the implementation of your research design. And you should be able to show the same thing. Once I deal with all these problems in the archival data, X looks exogenous. It looks balanced with respect to other stuff in the system. Okay, so that's why we often see this. So this is what we're trying to get towards. All right, a data set that looks like this somehow. Okay, so now we start thinking about research design. We have a common objective. There are a few different books that you can refer to on this topic. The one that I recommend these days is Joshua Ankrist and Stefan Pischke's Mostly Harmless Econometrics. There's a QR code if you want to go check it out. Um, Essentially, they go through some combination of all the various research designs with examples from prior research, often in economics, applied economics, and they talk through various issues in the application of each. Mostly everything is linear regression. And I honestly would advise whatever you do in your papers, start off with a linear regression, complicate it later. There are situations where the data generating process is exponential, like Poisson, right? Or it's a binary outcome. And so you might use a logit regression or something. Those methods can be relatively sensitive to model misspecification, the choice of control variables, all this kind of stuff. So if you can, I really advise starting with a linear model, and then you can try other estimators afterwards. But in your paper, it's going to be the most convincing thing for people if you show effects with really simple things that are intuitive, easy to understand, and not super assumption heavy. So this whole textbook works through linear specifications with research designs. Research design ultimately is going to boil down to arguments and assumptions and other people's judgments about whether your arguments and your assumptions are reasonable. Okay. You're never going to be able to show empirically that endogeneity is gone. You can sometimes show that it is present, however. So absence of evidence does not imply evidence of absence. Okay. Those are not the same thing. So you're going to have to come up with good, credible arguments. A credible research design is a convincing argument that you're isolating exogenous to the system variation in your treatment variable, your X. So there's a toolkit of methods. There's a whole bunch of different things you can do to try to do this or accomplish this. I mentioned randomized experiments. We're assuming that that's not an option here. So we're kind of working our way into some of these other methods. I'll talk about each of them to give some intuition for what they do. They are not mutually exclusive. You can combine these things in many cases. So like I can combine matching with instrumental variables and a difference in difference. I could do all of these things at once in some cases. The more of them you do, the more complex the assumptions you're making. So I don't advise doing too much of that. But the point is you can pair these things in many cases to deal with different types of endogeneity at the same time. So you can do, for instance, a difference in discontinuity design is going to combine regression discontinuity with difference in differences. Okay, so I can talk through that a little bit as we go. If you have questions about it, I'm happy to answer those too. So starting off, matching is not really an identification strategy. Okay, I've heard this many times. Technically, it kind of is, in that what it tries to do is after you've observed some archival data, you try to, so the case of matching, you pull out very specific individual units from the treatment group and the control group that look very similar on all their other characteristics to post hoc manufacture a data set that looks like it came from an experiment. That's fine. And of course, that works. You're kind of removing instances where the treatment was associated with other stuff to get to a subset of the population where it wasn't. The problem is you can only really do this for the things you get to see. You don't know what you don't know. There could be a whole lot of other variables where the subset that you've identified still differs markedly on these unobserved characteristics, but there's no way to know. And this is often a problem because there's no convincing argument for suggesting that they will be balanced on the things you don't see. You don't have a basis of argument here. So you're never going to convince anybody. So it's very rare these days. I don't think I've seen it in the last 10 years that somebody is able to publish an econometric quantitative paper strictly using matching. Reweighting is analogous. So IPTW is inverse propensity for treatment weighting. The idea there is instead of doing discrete matching, where we pick out specific units and match them in terms of observable characteristics to control units, what you do with reweighting is we're going to upweight basically observations that look more kind of towards the mean, representative of the sample, such that if you're like deviating in some sense, in terms of your characteristics, we're going to downweight you in the data set. Okay. So essentially what you end up doing is modeling the likelihood of treatment as a function of all the other variables that I get to see about you. You recover a prediction from that model, which might be a propensity score. This is one way of doing matching, by the way. And then with matching, you basically take equivalent propensity scores, like pairs of units that had the same propensity score, one in each group, and that's your matched sample. With IPTW, you just weight the observations inversely by their propensity for treatment. So you end up upweighting and downweighting such that they end up being balanced in their likelihood of having been treated in the effective sample at the end. So you can think about these as accomplishing similar goals. Just reweighting is a continuous version of matching in some sense. I've got a QR code in the top right. I have a paper that I published, not in IS, where the identification strategy was very much just weighting and matching. That said, you can at least see thought process, an example. That was a situation where there was no better data and there was nothing you could do because the treatment was something that always was going to come bundled with other stuff. It was whether a warehouse has robots in it or not. Okay, so there's really not much we could do to get away from the problem, but we did some reweighting and matching there if you want to check that out. I'm also recommending some packages you can use in R for these two specific things, match it and weight it, and I'll keep doing that with some of the other methods as we go. I'm typically an R user these days, and honestly, flexibility and availability of packages tends to be better there than in, say, Stata. Okay, so matching, again, you can combine it with other stuff, but it's something you can always, the nice thing about matching is it's something you can always do. Okay. It may not be enough on its own, but it's always an option. The next thing, instrumental variables regression. This is not used as often as it used to be. And this is, again, going towards some of the normative stuff in the discipline. It's fallen out of favor. And I think part of the reason that's happened is not because there's anything inherently wrong with it. It is that among all the research designs, this is the one that tends to, like matching, be very reliant on untestable assumptions and reliant on arguments that are often hard to make clearly. When I do see people submitting papers using IV, a common issue is that they don't take the time to clearly articulate their mental model and why this is a valid instrument given my mental model. So, what is an instrumental variable? It is an outside exogenous variable that affects my variable of interest, the one that is, I'm assuming, endogenous. And it affects it, right? Z is the variable I'm referring to here as the instrument. It affects X, but it has no other causal pathways to the final outcome of interest. It only operates through X. That's the assumption you need to defend for the instrument to be valid. And Z has to have a meaningful effect on X. Also, this is the relevance condition, okay? The challenge is I can always show the relevance part. So I can always run a regression of X on Z and show that, oh, look, there's a big significant coefficient there, and the model fit statistic is huge. Z has a big effect on X. That part's testable. The part that is not testable is the lack of other causal pathways to get from Z to Y that don't go through X. To the extent there are these other causal pathways, you're not really isolating the variation in your variable of interest, X, that is exogenous. Or at least you can't convincingly make that case. So this is very argument dependent. If you're going to use an IV regression, you need to be very thoughtful and careful to make a claim as to why Z is totally external to the system you're studying. It just so happens that this thing affects one of the variables in my model that I'm interested in, but beyond that, it has no plausible associations with anything else, including the outcome variable. There's no pathways by which it would matter. You need to make that case very convincingly in your paper. If you are fuzzy about it and all you do is make the argument that Z is going to have a big effect on X, and you don't get into enough detail about other aspects of the model, you don't make a case that Z is exogenous otherwise, you can't leave that fuzzy because then the reviewers are going to come up with like 10 different explanations about why this thing isn't going to be lacking causal pathways. They'll give other causal pathways. They'll just come up with them. So you need to be very careful and make the argument. Don't leave it open and vague. Otherwise, nobody's going to trust it. Okay. The pictures I'm showing you in the bottom right is just a directed acyclic graph explaining, how the instrument works. So Z's affecting X. X is the thing I actually care about. Maybe it's got a confounder U that's driving its relationship with Y. The point is, if I first regress X on Z, I'm projecting X into the subspace of Z. The projection idea is why I've got vectors on the left showing this geometrically what's going on. This is two-stage least squares. If you recall from regression, when I regress one variable onto another, y onto x, I'm projecting y into x's subspace, and then anything that is orthogonal, so any component of y that is perpendicular to x's vector ends up in the error term. So what I get back is like I'm basically taking that vector y green, right? And I'm projecting it onto x. It's a scaled version of x, right? And any of the other dimensions of y that are not captured by x's subspace end up in the error term. It's a projection. So what I do in the first stage of my 2SLS is I'm taking my x vector and projecting it into a subspace z that is now orthogonal to all the other stuff like u that I might have been worried about before. Okay, so I'm basically taking the component of x that is clean, which is associated with z, and then implicitly what goes into the error term, I'm throwing away all the bad stuff that's associated with, say, u. This is YIV. You can think about it like a surgical knife, and I'm carving out some of the variance from x that is good variance, so I can discard the bad variance. That's kind of what's going on here. But all of this depends on you making the case that I don't have these other causal pathways. To the extent I do have other causal pathways, I'm going to keep undesirable variation is going to be left over in X. Okay. So IV is not that common these days. DID, on the other hand, is everywhere. People, I think, unfortunately, treat it like a panacea to these problems. Part of the reason I think it's very favored these days is that it is also very, like, fairly easy to understand what's going on. It's not a randomized experiment, but I do have like a treatment and a control group, and I'm seeing them over time, and the treatment turns on at some point in the middle. And to the extent that the treatment and the control group, their outcomes looked very similar before the treatment started, then the control groups are pretty good counterfactual, right, for what would have happened to the treatment in the post-treatment period. This concept makes sense. It's very intuitive. I'll note a couple of things here. One, it isn't necessarily the case that you require time series data to use diff and diff. So it doesn't need to be that you see things over time. You can also see them cross-sectionally, let's say across geographies. They just have to vary over some other dimension. It doesn't need to be time. Time is typically what we look at, what we think about though. Couple key assumptions for this method to make sense and to give you a causal effect. So the first thing is the control group needs to somehow mirror the treatment group before treatment turns on. That doesn't mean that they have to match in levels. They don't have to be sort of the average outcome value doesn't need to be the same between these two groups. The trend in that outcome needs to look the same. So they can be shifted in levels, but following a parallel path. The reason is it's not that hard to adjust for the intercept difference, essentially. So the intercept in my DID is going to basically account for that level difference that's happening. But as long as the trends are mirroring, you can think about this as if you were to take a first difference in the series, that first difference looks flat. Okay, so the slopes have to be the same. This is for canonical difference and differences. The second thing, an issue that people often overlook. So the first one is, by the way, this is the parallel pretreatment trends assumption that is common at DID. The second one that people often overlook and don't think too hard about, but need to, which you can't see in the raw data, it's a conceptual problem, is stable unit treatment value assumption. Basically, the control group needs to actually stay in the control. They don't get treated. The problem there is you can get into all kinds of situations where the treated group's treatment effect spills over onto the control group in some way. So examples of this, if I'm looking at companies that are selling products and they're in competition with each other to make sales, when I treat one and its sales go up, their competitors, their sales could go down as a result, right? Because they've lost sales to the competitor. In this situation, you're not getting a good counterfactual for what would have happened in the absence of treatment because the control group has been causally affected to have their sales drop. That's a problem. That's a SUTVA violation. Similarly, spatial spillovers. If I have two geographies that are neighboring and I treat one and something happens here, let's say crime gets affected and goes down, maybe the criminals move next door. So now the control group has been affected too by my treatment, and it's no longer a good counterfactual. You can't see that in the data. It'll look like control group drops, treatment group goes up, but maybe that control group fell because of market-wide trends and would have happened anyway. You can't tell. So this is one that you have to argue conceptually. Okay. And it depends on your understanding of the data generating process. The newer one that's come up since like 2021 has become an issue that people realize that all the logic of canonical difference in differences, which is a single shock that applies to a subset of units at a single point in time, that kind of starts to break down once you start looking at situations where treatments are happening in a staggered way to different people at different times. So different states adopting it's the same policy at different points in time, that's staggered difference in differences. If you use traditional estimation, an OLS regression with a treatment dummy, it's not going to work properly, or it may not work properly. The main issue is staggered treatments mean forbidden comparisons can happen. So there's a visual here that's kind of demonstrating what the problem is. If you think about a unit that gets treated late, my cat just showed up. If you think about a unit that gets treated very late in the process, implicitly, traditional OLS, it's going to do comparisons between like difference and differences comparisons before, after versus after treatment for that later treated unit. And the contrast is going to be things that are not being treated right now, including things that were treated before. So some of my control group for this particular little DID that's contributing to the estimate, it includes things that have been treated in the past. And if treatment is not a step function in the outcome, if it's gradually evolving, then treatment may not have finished manifesting, right, for one of these controls. And then what I can get is this one's still going up faster at this point because it's like growing exponentially or something, faster than this one's going up after its treatment. And then we get a negative treatment effect actually, despite that the reality is that it's positive. So these forbidden comparisons are the main problem with staggered diff and diff. And so there's estimators, like a whole slew of them, like 6 or 7 at least, that people have come up with that avoid this problem. I'm just listing a couple packages here that implement some of these things. You can check it out if you're curious and you're in the situation. And then I will get to synthetic control. This kind of came to be in like 2010. This is uh, I guess, among all methods, this is the most recently developed one in economics. Before synthetic control, the last thing to be developed was RDD back in the 60s and 70s. Okay, so there was a long period of nothing happening, and then all of a sudden we got a new method. This comes from kind of political science and case control studies, where you basically have a situation where there is one treated unit, and it's very hard to come up with a counterfactual for that one unique treated unit. Like the state of California passed a tobacco law, and nobody else had ever done that before, and tobacco's and California is really weird. So how do we really think about studying that causal effect? It's all about, okay, there is no good control group, even for a DID, but maybe we can synthesize one. If we take a weighted combination of the controls we do get to see to make something that looks just like the treatment in the pre-period. So maybe like 3 times New York plus 4 times Texas plus -1 times Iowa, whatever was happening in that weighted combination, that starts to look just like California in the pre-period. And you can empirically test that because it's basically a predictive model in the pre-period. Can I predict accurately the treated panel's outcomes in the pre-period using the controls? Of course, you get into concerns about overfitting and other stuff with machine learning, right? But the point is, this is the idea. And then you get a synthetic control that you make up from the data, which you then use for inference. And there's a variant of, I mean, there's ways to get uncertainty estimates from this that came later. As of, I think, 2019, there's now a mashup synthetic DID that Susan Athey came up with that combines this idea with difference in differences, where you basically get a synthetic counterfactual for every treated panel. You can get a synthetic treated outcome for every control panel potentially, and then do a DID on those synthesized panels. So it gets quite complicated, but this is there are packages that implement that now that you can check out. So that's synth DID. And that is something I've seen lately popping up in IS papers. And then the last one I'll talk about is regression discontinuity design. This is, experiments aside, probably the most convincing research design for a causal effect, in part because it is something that shows up in visualizations very clearly. It's all tied to an arbitrary threshold, a rule, where if you're just beyond that threshold, you're treated. And if you're just below it, you're not. This is usually a function of some human-made policy or like a machine learning algorithm with a threshold that triggers something to happen. Like you're going to be recommended if you just surpass a predicted value threshold, for instance, or you're elected into office if you have just passed the majority of votes. Like sort of these arbitrary rules where you see a discontinuous shift into treatment from control right as you cross that threshold. So It's rare that you see published papers that use these methods because having relevant arbitrary thresholds that then can tell you something about a meaningful research question, needing those two things together is not that common. But it does happen sometimes. Key things here are visualizations become very important. So plotting the data and showing evidence of a discontinuous effect around the threshold is important. The second thing is there are lots of tests that you would do empirically to make sure things are valid. So one is just like with an experiment with a balance check, you're going to show that too with your RDD sample. Right around the threshold is everybody statistically comparable in all their characteristics, aside from the treatment status. You're supposed to be as good as randomly assigned in the proximity of the threshold. The other thing is that needs to be true is people can't be aware of the threshold and able to adjust their status. So if you see selection on the threshold such that maybe there's some benefit to being treated, right? If we're talking about passing an age threshold to get retirement benefits or something, people might lie about their age if they could. That's a problem because they're going to bunch just above the treatment and everything falls apart. So there's tests for that. Do you get bunching around the threshold? That shouldn't be true if this is a valid design. It's not common as a method in IS because it's rare that you see instances where it makes sense. But there's a QR code here. I do have one recent paper looking at elections in online community moderator positions and the effects of that on career prospects, where we use this methodology if you want to check it out. And so RD robust is probably the main package to look at in R for this, and RD plot is to create the visualizations that go with it. Okay, so that's a broad overview of methods. I'll quickly just go through some things, and then I'll wrap up here and can take questions from you guys. So, some various things on disciplinary norms these days in IS journals with quant methods. So, particularly causal inference, econometric stuff. So, the first is panel data and matching are kind of a baseline. I understand it's not always the case that you're going to have time series data. But if you don't, and then you don't have some other credible research design that helps you, like a regression discontinuity or a valid instrument, then you're going to get into trouble with people because you're going to be in the world of matching, and there's nothing else you can do except matching. And people are very likely to be unconvinced. Okay. So this isn't to say don't work on a problem where you don't have time series data. But it is to say that be prepared for making very good arguments, conceptual arguments about why it's okay what you're doing, or at least be good about documenting the threats to inference, right? Like what the problems may be here. Um, don't just throw control variables in, and this is advice not just for authors but for reviewers too. Make sure there's a good reason for those controls to be there because the controls can make the results. If you condition on the right set of factors, it's often possible to show whatever you want. So this is something to push back on, is to demonstrate that results are not super sensitive to the choice of the control set. And I often get very leery when I come across a paper submitting regressions where there's like 20 control variables, uh, and they're not well justified. I'll immediately ask, like, show me like how sensitive is your result to alternative, like dropping and including different controls. It shouldn't be bouncing around like crazy unless there's a really good reason for having that control there. Like, oh, we need a condition on this, otherwise it would be a confounder. And here's why it would be a confounder. Like, so justify your control variables. Uh, these days, there's a huge like expectation from reviewers that you're going to show robustness in various ways. So it might mean show the same result with a different research design. That's not that common because that's a ton of work. But what is more common is use a different measure for the same construct and show that you get a very similar result. Or, instead of a log linear regression, do a Poisson regression and show you get a similar result. That your result's not super sensitive to these choices. That shouldn't really matter too much. The other thing is this idea of placebo treatments. So that can mean, like in the data, artificially change when the treatment's happening in a random way and show that that artificially changed treatment doesn't have an effect in the data because it shouldn't. So it kind of tries to show that the results are not an artifact of your data and the way you approached it. The other thing you can do is if there are outcomes, things that you know should not be affected by the treatment by design, run a regression and show that you get a null result. If you don't, that's worrying. Okay. So these things are expected commonly. I already said this first one, so I won't hammer it again. If you're using IV, be sure to clearly argue it and why it's valid and excluded, why you don't have other causal pathways in your model. For time series stuff with DID or synthetic control, you should assume you're going to present event study plots. So this is also known as relative time models for some people. But the point is, you can think about taking one of your time, you can do a whole bunch of mini DIDs. So this period relative to that one, treatment versus control, what's the diff and diff? And you can do that at many different time contrasts. In the lead up to and after treatment starts, you get this event study of effect estimates. You should expect to present that visually, not just in a plot, because people get worried about the trend of estimates and whether it's indicative of like selection and the timing of treatment, et cetera. So that's expected, and I'm recommending some functions you can look at for generating those easily. And then standard errors, how you're calculating those is become increasingly something people worry about. So you're not getting like artificially inflated effect sizes. Um, there's reasonable guidance on this now. This is a conceptual problem, a thought exercise about what's the sampling, like basically what is the sampling from what population, et cetera. General rule, if you're looking at some kind of treatment, the scope at which treatment is applied. So if treatment happens at the state or at the organization as opposed to at the individual level, you should cluster by the unit of treatment. Okay, so if I have a bunch of data on companies, but there's like a government policy change that happens at the state level or the province level, I should cluster my data by the province or the state, not by the company. Okay, this works fine until you get into territory where you don't have very many clusters. Like there are only 50 states in America. That's like borderline. As soon as you start getting into a situation where you have like, 25 police districts or something like this, now you're getting into an area where you're going to get biased standard errors if you use clustering, downward biased, makes your effects look bigger than is real. And so there's corrections for that for dealing with small cluster count situations. And again, I'm giving you a recommended package to check out for Wild Cluster Bootstrap is one example of a correction you can do. Other things that I would advise, or just to be aware of. Um, as an editor, I generally weigh the rigor of a paper in terms of the methods against the novelty or interestingness of the question. And I allow some trade-off in my head. So if you have a less novel or interesting question, I'm going to have a very high expectation for rigor. Like I need to be very convinced that you're precisely estimating the causal effect of interest, such that at least the magnitudes are meaningful and maybe useful to people to know those magnitudes. If you are looking at something nobody's ever thought about before and there just isn't great data yet, then I'll maybe sacrifice a little bit what I'm maybe willing to tolerate weaker research design and things just to be able to get a paper out that's making people start to think about this problem. So gauge your own paper based on these criteria to think about how much more do I maybe need to do with the methods. Visualize your data before you start doing any kind of regressions. Often, I can't count the number of times I've seen weird things in the visualizations that made me go back and check and realize either an error somewhere or that I had misunderstood something about the data. Those visualizations often are nice to put into the paper itself anyway, and often they can help you tell your causal story. I mentioned already you should try to start with linear regressions before you complicate things when it makes sense. Sometimes there's no way a linear model will make sense, of course. Increasingly, there's a lot more multi-method research happening. So generally, this is a good idea. So sometimes you can't fix all the problems with econometrics. It's just no way to do it. So don't give up. Maybe the solution is go interview some people or do some surveys, or maybe it's run a lab experiment. Okay, so think about multi-method as a way of like complementarity among methods as a way of dealing with some of these problems if there's no way with your current data to solve this issue. Be careful because details are very important. So if there's a lot of typos, there's unexplained things going on in like the regression tables, like observation counts are shifting around. A lot of the stuff, if it happens too much, then people can start to get concerned about sloppiness, and then they wonder, well, maybe you're sloppy in your research too, and it makes me less convinced about what's going on. So this is like death by a thousand paper cuts kind of situation. Be as transparent as you can. So if you can, these days, I really do advocate like put your code and data into a repository before you even submit the paper and give a link to the repository if you can do that, because that gives reviewers so much more confidence in your research that you're being transparent like that. They can just go look at it. And often they won't even go and look, to be totally honest. But the fact that you've done it gives them some confidence that you were willing to do that. Okay. Last one's kind of an aside, not that important, but if you are doing prediction stuff, make sure you're looking at predictive error evaluation. Don't look at regression coefficient significance and then say, oh, look, that's significant, therefore it's predictive, because those two things are very different things. And sometimes I see people modeling these two things in their papers. Okay, so I'll stop there. I want to leave a little bit of time for questions if there are any. But I hope this was helpful.